When we see an oxygen that has two single bonds to two hydrocarbon groups, that is known as an ether. Now, an ether is similar to an alcohol, except instead of having an oxygen-hydrogen bond, it has another oxygen-carbon bond. Now, these two carbon groups that are bonded to the oxygen can be the same or they can be different. And if they are different, we use a prime on the R group to indicate those two carbon-containing groups are different. Now, like alcohols, the oxygen has two single bonds, which stand for 4 electrons, and then it also has two lone pairs that we don't expressly write typically. So our bond angle here is going to be less than 109.5, and ethers are going to have a bent structure. The simplest ether is dimethyl ether, where the oxygen is connecting to methyl groups. And I just want to point out something about how we write this structure. On the left-hand side, our methyl group is not written as CH3, it's written as H3C. And that's because when we draw the bond between oxygen and the methyl group, we want to be absolutely certain that it's clear that the oxygen is bonded to the carbon and not to the hydrogen. And in our ball and stick model, we clearly see the bent structure of the ether. The oxygen is red, carbons are black, and the hydrogens are white. Another important ether is diethyl ether, which was used as the first anesthesia in surgical procedures. Again, we see this bent molecule here. The oxygen is red. This bond angle is going to be slightly less than 109.5, and the carbons are represented by the black. Like the structure for dimethyl ether, when we write the connectivity between oxygen and the ethyl groups, on the left-hand side is written backwards, H5C2 instead of C2H5, because again, we want to be absolutely clear that that oxygen is connected to carbon and not hydrogen.